finally time to talk about drag. We don't always neglect air resistance, just usually, and there's often good reason to neglect air resistance. But now we're going to actually focus on air resistance, what it is, and how to calculate it. Now, really, drag is the name that gets applied to several different forces. We are going to focus on drag as it applies to air resistance. There's also liquid drag, fluid drag, that has a different equation and applies when something is moving through a liquid. We will not apply that this semester. That's usually a Physics 2 thing. We are going to look at this air resistance form, but we're still going to use the letter D. We're going to call it drag. There's several different constants and coefficients that go into this calculation. We're going to look at them one at a time. So D is the magnitude of the drag force. We've mentioned before that whatever direction an object goes through the air, the drag force will oppose that motion. So if you are firing an arrow that way, then the drag force on the arrow will point the opposite direction. Oh, there's a lot of arrows. That's fine. So, going through these terms one at a time, the very first is just plain old 1/2 sticking out in front of the calculation. The second is the drag coefficient, CD. This is a term that depends on the geometry of the object that's going through the air or gas. And it can vary depending basically upon its aerodynamics. So if you have a very aerodynamic shape, this will be a smaller value, closer to 0. And if you have a very unaerodynamic shape, like a cupped sort of shape, if it's going that way, it can be a number somewhat greater than 1, maybe close-ish to 2, maybe. These numbers can be calculated or estimated by various means. We are not really going to do that in this class. We are just going to use a general approximation of 1/2 for CD. Now that is different than this 1/2. So we have a 1/2 here all the time. Everybody has that. We are going to use a 1/2 here in addition. In other classes, you would look up or calculate or apply a different value here instead of a 1/2. So 1/2, 1/2. The next value is rho. This is the Greek letter rho, R-H-O. It's not a P, sort of a slightly curly sideways character and not a P. It's actually the Greek R instead of a P. This is the density of the gas or material that the object is falling through in kilograms per meter cubed. Usually we're talking about air. Air has a density of 1.2 kilograms per meter cubed, 2 sig figs. Our book and Mastering Physics uses the 2 sig figs. If I give you 3 sig figs, it'll round to the wrong value, so we'll just use 1.2. A is one of the most important things to calculate when we're doing these problems. This is the cross-sectional area of the object. So it depends on which direction the object is moving through the gas. So if you have a cylinder and the cylinder is moving that way through the gas, then you want to take a slice through the cylinder. If the object is moving this way through the gas, you want to take a slice through the cylinder perpendicular to that motion, right? So think of a plane slicing through the cylinder, and that slice is going to make a circle, right? So if you know the radius of that circle is r, then the cross-sectional area is going to be pi r squared. But if your cylinder is going this way down, and you take a horizontal slice through this, Well, this horizontal slice is now going to be a rectangular shape. And so it's going to depend on twice the radius times the length or height of the cylinder, whichever you want to call it. We'll call it height. So A is going to be equal to 2RH in that case. So you have to think about the shape of the object that's passing through the air as well as the direction it's going. Think about a cross section that you're slicing through that shape, then calculate the area from that. The final variable is the speed, v, and it depends on the speed squared. So if you double the speed that the object is going through the air, that speed it gets squared, so that 2 that you're doubling with gets squared, so the drag actually increased by a factor of 4. So drag is very dependent on the speed of the object that's passing through it. So let's just do a quick calculation. Let's say that an object, particularly a soccer ball, is being dropped through from a third-story window, I say, and its speed is going at 5.00 meters per second. We're going to use our standard coordinate system here. We have a radius of 11.0 centimeters. And we're trying to figure out first what's the drag force and then the overall acceleration. So since this is two different components, we can go ahead and calculate a number for the drag force. So we have 1/2 times, we're going to use 1/2 for CD. We're going to have our value for rho is 1.2 kilograms per meter cubed. Let's think about our area here. The cross-section of a sphere, really no matter which way you cut it, is always going to be a circle. So this is going to be pi times the radius 0.110 meters squared. And then finally, we're going to square the speed as well. So the speed is 5.00 meters per second squared. So the drag force, when we multiply all that out, we get 0.5 times 0.5 times 1.2 times pi times 0.11 times 5 squared. Okay, so I get 0.238 newtons. And of course, if you multiply all this together, you can confirm for yourself that the units are newtons, because it is a force. Okay, so part B, we are asked to find the acceleration. Let's do a quick sketch of a free body diagram. The ball is moving downward, so the drag is pointing upward. Weight is pointing downward. We are no longer touching the ball. We have already dropped it. It's not immediately obvious which is greater, although it's not hard to figure out that weight will be greater. So these are our two forces. So we're going to be doing sum of forces in the y direction is equal to MAY. So that means that drag minus weight is going to be equal to MAY. All the forces pointing up get a plus sign. All the forces pointing down get a minus sign. So AY is going to be equal to D minus W over M. So that's going to be equal to, we already have the drag force. The weight, the mass we have here, right? So that's 0.30 kilograms. We have to convert from grams to kilograms times 9.80 newtons per kilogram. And we're going to divide that by 0.430 kilograms. And we're going to end up with, let's see here. I seem to get negative 9.24 meters per second squared.